Hello, I'm Scott Jenkins, Senior Editor at Chemical Engineering Magazine. Thank you for joining us for our webcast on environmental risk management. We hope it will be informative and interesting for all of you. Environmental risk management involves managing complex processes while avoiding catastrophic events that result in safety hazards, environmental damage, or economic loss. Practitioners need a clear framework that addresses end-to-end environmental risk management from prevention to remediation. Today's speakers will address topics including the key steps in organizing a process safety management system, minimizing site assessment costs utilizing EPA guidance, site sampling and surveying designs, risk and non-risk goals for remediation, and remediation technologies. For today's program, we're going to hear from three speakers. The first will be Ian Sutton, a chemical engineer with over 30 years of design and operating experience in the process industries, providing services in all areas of process safety and risk management, including audits, incident investigation, hazards analyses, operating procedures, and management of change. He is principal at Sutton Technical Books and formerly a technical lead in process and technical safety at AMEC, and also a senior process safety engineer at Fluor Daniel. He's a recognized authority on process safety management and regularly teaches courses on the topic. He's also the author of several books on process safety management. Following that, second, we're going to hear from Mark Burns, a senior project manager for CH2M Hill at the Hanford Nuclear Reservation in Richland, Washington. He's responsible for the remediation of one of the world's largest groundwater and Vadose zone chlorinated solvent plumes and is responsible for chemical and radioactive source area cleanup. He holds a master's degree in geology from Portland State University in Oregon and a bachelor's degree in geology from the University of Colorado at Boulder. He's a registered geologist and hydrogeologist in the state of Washington and is the author of 3 university textbooks. And then finally, we're going to hear from Trip Fisher, who leads BSTI's environmental consulting group in its corporate headquarters in Cochranville, Pennsylvania. He specializes in conceptual site model development, environmental policy, risk assessment, and remedial strategy. Prior to joining BSTI in 2009, Mr. Fisher served as a hydrogeologist and environmental engineer for the state of Delaware's Department of Natural Resources for 11 years. During that time, he developed and revised numerous environmental regulations, policies, and guidance documents, and participated in many multidisciplinary work groups within the agency. In addition to these positions, Mr. Fisher served as co-team lead for the Interstate Technology and Regulatory Council's Light Non-Aqueous Phase Liquid team, and also chairs the ASTM Subcommittee on Environmental Corrective Action. Mr. Fisher is a professional geologist with an undergrad degree in geology from Westchester University in Pennsylvania and a master's degree in engineering science from Penn State University. So the 3 presentations will last about 45 to 50 minutes or so, and that will be followed by a question and answer period. At the left of your screen, you should see an area where you can type and submit questions to the speakers. You can submit questions throughout the presentation, and once all 3 speakers present their slides, we'll try to answer as many questions as possible. If we don't get to all of them, we'll try to respond by email after the program is finished. If you experience any technical difficulties during the program, you can type that problem into the same chat box on the left of your screen, and someone will assist you. And this program will be archived for future viewing and will remain free of charge. You will be able to use the same URL to reach the archive program that you did to reach this live program today. Finally, I'd just like to thank Novell, an Elsevier company, for sponsoring today's program. Novell is a cloud-based information platform for engineers, and they've allowed attendees to view the presentations at no cost. So thank you. And with that, I'm going to turn the program over to the speakers. So Ian, would you please go ahead?
Okay, thank you, Scott. This is Ian Sutton, and I'm the first speaker. The overall title of this presentation is Avoiding and Handling Environmental Incidents. I'm sure we'd all agree that the best way of doing this is to prevent the incidents from occurring in the first place. One way of doing this is to use the well-established methods of process safety management. Process safety management isn't strictly speaking, just a safety program. It also covers environmental and economic issues. It's well established. It's been around for many years, and it's successful. And it covers a wide range of industries. As you can see in this second slide, I start by saying it's a management system. It is basically about how you manage safety and environmental issues, and it's not just technical. It does cover safety, environment, profitability. It's been around for many years, and the formal programs, at least in the United States, started in the sort of late 1980s, early 1990s. Different companies and different regulators have their own versions of PSM, of process safety, which I've called dialects. But the key is they're pretty similar. As you go from company to company and regulator to regulator, the differences are quite minor. What is the definition of process safety management? Well, I've put up here two definitions. The first one is from the Center for Chemical Process Safety, which is part of the American Institute of Chemical Engineers. And they say it's the application of management systems to identification, understanding and control of process hazards to prevent process-related injuries and incidents. And I would add to that environmental incidents. The key word there is process. It's not to do with occupational safety like slips and falls and vehicle movements. This is my definition. The second paragraph is my definition of process safety. It's an ongoing process. It never finishes. It's not a program you do and then finish. It's living. It involves all managers, employees, and contract workers. And again, the word employee is used in the broadest sense. It aims to minimize uncontrolled change from design or operating intent and to keep the process within safe limits. That if you can keep the process within the safe limits, you will not have a process safety related event. This slide, called Safe Limits, is really a key to what I'm talking about. What I've put up here is a variable. It could be anything. It could be a temperature, it could be a pressure, it could be the level in a tank. It really doesn't matter. It could be a flow rate. And I've put some range numbers on it. In the middle of the range, we have what I've called operating range. That's where that variable will normally be operating 99.9% of the time. That's where your temperature or pressure or level will be. In this example, which is fictional, I have an operating range from 235 to 245. And the operators and supervisors are free to operate in that range and in order to make the most economic operations. They know that if they stay in that range, they will not have any safety problems. If they exceed the operating limit, 245, or go below 235, they're not immediately into a safety problem. There is an area what many people call troubleshooting. The process is not operating well and you're losing money. But you're still technically sort of safe, but you probably need to be taking action to try and bring it back inside the operating range. If you go beyond that, in this case 275 or 210, by definition you're unsafe. It doesn't mean you have an emergency. You may have plenty of time. Because if the value of goes to 276, you must take action. The option of doing nothing is not an option. It also means that if you want to go beyond 275 and you want to operate at, say, 280, in order to do so, you have to implement the management of change program. This example shows two emergency limits, the high and the low does have no value. What it's saying is if you reach 310, whatever the units are, you must take immediate action. You don't have time to be thinking about what to do. There's a profound distinction between occupational safety and process safety. Occupational safety is what most people think of when they hear the word safety. They say trips and falls, slips, vehicle movements, PPE, all that kind of thing. And many of us are very familiar with the safety triangle, the idea being you have 10,000 near misses, 1,000 minor injuries, and so on. And if you can reduce the number of near misses to 9,000, so it sort of ripples up, and you have just 9 fatalities. It's misleading. This triangle doesn't really work with process safety. Company after company has had an excellent occupational safety record, and then to their total surprise, they have a catastrophic accident. I've seen it throughout my career. Therefore, having a good occupational safety record, like recordable injuries and that kind of thing, does not mean you have a good process safety program. But the opposite usually does apply. This is a lengthy quotation. After the Texas City explosion in 2005, the refinery, BP had a refinery in Texas City, and there was a bad explosion. Personal friends of mine were injured, and there were many fatalities. And James Baker, who had been Secretary of State in the first Bush administration, headed up an inquiry. And this is what he wrote. It's a lengthy quotation, but it's worth reading. Basically what he said is that BP, the manager of this refinery, had a good safety record and it was getting better. And then they had a terrible explosion. And the lesson to be learned is that it's a different kind of management system. What is process safety in more detail? As I said earlier, different companies organize it differently. Typically there's around a dozen elements. But most major oil companies and chemical companies have their own version, their own dialect, if you will. And most regulators also have their own version. This one here, though, is the one that's most established. In the United States, OSHA came out with these 14 elements in the year 1992, and the EPA issued their own regulation in 1996. The EPA regulation is very different in terms of the sort of mechanics of compliance, but the two programs have an identical technical basis, and they each have 14 elements as shown here. And this organization is fairly representative. In the interest of time, I've picked on just 4 of them, but it's important to understand that they're all important. They're not more important than each other. They are interconnected. An obvious example will be operating procedures and training. You can't train people unless you have procedures, but there's no point writing procedures unless you train people. It's two sides of the same coin. Employee participation, here we use the word employee in a very broad sense. All workers, managers, contractors, anyone, consultants, anyone who has involvement is an employee. It's absolutely crucial. And it's called participation, not communication. And really, as this goes, so the program goes. If people are participating and making suggestions and being involved, it's bound to go well. But if they treat it as just something else on the shelf, it will not go well. It's important that all employees have access to the information I showed earlier as it affects their job, particularly the safe limits. And that information must be really accessible. If you have a bad accident at 2 o'clock in the morning, you don't have time to be reading books. I've picked also on process hazard analysis. When process safety was new, the emphasis, and quite rightly, was on process hazards analysis. The idea being that you cannot fix a problem unless you know what they are. There are many methods that can be used for process hazards analysis, and they all have their place, and they're all good at certain times. The HAZOP, Hazard and Operability Study, became the most common because it's very, very thorough. But once more, you have to have numbers. You have to know safe limits. Otherwise, you get circularity. You know, could high temperature cause an accident? Or what is high temperature? What's that temperature that could cause an accident? So again, you need numbers. You do hazard analysis to find the causes of a potential incident. You try and determine the consequence of the safety, environmental, financial, what would happen if it happened. Likelihood, you know, is it pretty common or is it once in a blue moon? And then you analyze the safeguards, process safety relief valves, instrumentation, that kind of thing. I said that HAZOP has been the most widely used system for many years. It seems now that both the time method and barrier analysis is sort of taking over, and more companies are using that approach. It was an approach developed by Shell about 10, 12 years ago, and is now becoming quite widely accepted. Management of change. All incidents are caused by uncontrolled change. If you can keep the process within the safe limits, you won't have an incident. You must know those limits. You must understand the types of change. The one we think of the most is initiated. Someone says, I want to change something. I want to raise the temperature. I want to change the type of stainless steel. There are other, in some ways, more dangerous kinds of change. Non-initiated, like corrosion. Things are changing, you don't even know it. Temperature changes are a cause of many accidents. People tend to be fairly casual about those, but they can still lead to accidents. Emergency changes are made very, very quickly because you have to do something quickly. And one of the things that's happened in the last, say, 10 years, originally management of change was seen as a technical program to do with temperatures and materials of construction, that kind of thing. Increasingly now, companies are putting administrative change inside the MOC program. If we increase the number of people on the shift or decrease, that has to go through MOC. Finally, the process safety systems recognize that things can go wrong, and therefore one of the elements is emergency response. There are two kinds of initiating event: internal, something goes wrong within the process itself, or external, as an outside event that impacts your facility, like an earthquake or maybe hurricanes, that kind of thing. And you have different layers of response. Emergency operations is where the problem is handled by the local operators, and they take care of it. And probably the overwhelming number of emergencies are stopped at that point. If they do lose control, you go into local emergency response, which is where the whole chemical facility, a refinery, whatever it is, pipeline, will get involved, and you're going to get fire teams and that kind of thing. General emergency response, you're bringing in outside agencies like fire departments and police departments. After the emergency, you have recovery and investigation and follow-up. During an emergency, it's important to rely on your instruments. Psychologists say that human error rate is at least 20%. If you ask someone to do something during an emergency, it's a polite way of saying they panic. So if you ask someone to do 5 tasks during an emergency, the chance of them getting it right is 0.8 to the power 5, 33%. And they're almost bound to get it wrong. The best way of managing emergency response is just to practice, just to have drills and repeated practices. So I think I reached my conclusion. The person on the left is Trevor Kletz. He passed away last year. He was a mentor to many of us, and I'd like to use this presentation just to acknowledge his contribution to our industry and to me personally. And he was one of the founders of process safety and taught us that we must manage the process if we want to make sure it doesn't go awry. We must involve all workers. We must know our safe limits, and we must have a good management of change program. So at this point, I'd like to pass the ball to Mark, because he will be moving into response issues that I've just been discussing. Thank you very much. Mark, you've got it.
Yes, thank you very much, Ian. My name is Mark Burns, and I am a senior scientist. I work for CH2M Hill here at the Nuclear Reservation at Hanford site. And my talk today is on the topic of site assessment. This diagram here basically shows how our 3 presentations that are being given today fit together. So Ian's talk on process safety management, in case there were an accident that occurs and chemicals were released into the environment, emergency response would then be performed. If the conclusion from emergency response resulted in contamination impacting the environment, then site assessment and site characterization would be performed, which is the topic of my talk. This is primarily designed to define the 3-dimensional distribution of contamination in the environment, and also to collect data to help support the screening of remedial alternatives and the performance of a baseline risk assessment. Following my talk, Trip will be talking more about remedial technologies that can be used to help clean up the site. So with that understanding, I'll now proceed with my talk. So why is site assessment performed? As I mentioned a moment ago, one of the primary reasons it's performed is to define the 3-dimensional distribution of contamination within the environment. as well as to define the direction and the rate of the contaminant migration. We also perform site assessment to collect data to help support various types of modeling. That could be groundwater modeling, surface water modeling, air modeling, as well as ecological and human health risk assessment, the screening of remedial alternatives, and also remedial design. Yes, there are many, many site assessment technologies out there. There's always the question of how do you pick which method to use and how much data do you collect with each of the methods. I'm hoping the conversation today will help you a bit with this. So before developing a site assessment approach, you need to ask a variety of questions. One of them is what questions need to be answered. Also, what types of data and what quality of data and what quantity of data are needed to resolve each of those questions. And are there any types of screening technologies out there that can help minimize costs? The two photographs on the right side of the slide show a couple of different types of geophysical surveying techniques that can be used as screening technologies. Other questions to ask are, is a statistical or a non-statistical sample design most appropriate for your project? And in some cases, it might be a combination of both. This is a process flow diagram that I developed here at the Hanford site along with a variety of other scientists. And this process is for developing a defensible site assessment approach. So I'll be talking you through this process here shortly. I want you to keep in mind how I have integrated heavy involvement of the decision makers early and throughout the process. Decision makers are representatives of the Environmental Protection Agency, your state regulatory agency, as well as your client. So this first box is a planning meeting. This is where the project manager will meet with a small group of advisors. We will select what's called a facilitator. I'll talk about that in the next slide. We'll also select a data quality objectives team. This team is normally 5 to 10 people composed of scientists and engineers, sometimes like a quality control specialist and modelers. And we'll also define schedule and budget in this meeting. The facilitator is the one who carries the team through the sample design process. This person that you select needs to have a very good understanding of the scope of work to be performed and needs to have excellent communication skills. The scoping process, this involves a review of historical photographs and maps and data sets and historical documents that will help you pull together information about historical spills and releases that have occurred in the environment, historical waste handling and disposal practices, identify the types of chemicals that are currently used at the facility or have been used in the past at the facility, as well as the estimated volumes. We also perform interviews as part of this process. Particularly important to interview historical workers who can scratch their head and go, I remember about 10, 15 years ago, we did have a spill out in this area, and this is how we cleaned it up, and this is where we put the waste material. That type of historical information is crucial. The results from the scoping process, we use that to help identify our contaminants of concern for the facility. It's particularly important to not miss a contaminant of concern because this can lead to human health and ecological impact in the long run. And we also develop a conceptual site model. I'm pointing to a conceptual site model taken out of my textbook. The conceptual site model identifies the source or sources of contamination, the human and ecological receptors, the pathways for contaminant migration, and the pathways at which the receptors can be exposed to the contamination. Next, it's important to also perform a site visit. Oftentimes you will see things when you visit the site that you were not able to pick up from the historical documents. The next box is the decision maker interviews. So you will be interviewing the EPA representative, your state representative, as well as your client. The important and focus of this is to identify their specific issues and concerns that they have about your project. You want to interview them separately so that they can share with you. Maybe sometimes the state and the EPA do not agree on certain topics. By interviewing them separately, you can get the true feeling that the agency might have. You're building relationships with these interactions. That's actually absolutely crucial. You need to get these agencies to trust you. The next box is called the Global Issues Meeting. This is in case two of the decision makers disagree on a particular topic. For example, the EPA might want to clean the site up under the CERCLA process, and maybe the state wants to clean it up to RCRA. So you'd have this meeting to clean up those disagreements. Next box is the preparation of a strawman data quality objectives summary report. The data quality objectives team prepares this. They go through the 7 steps of the EPA's QA-G4 guidance manual and take a first cut at going through this. We have tried here at the Hanford site several times to go through this process with the regulatory agencies, and it led to very, very, very long meetings. And we concluded it actually is easier to just give a first cut at it and then go to the next box here, which is where we present the strawman data quality objectives summary report to the regulators in a conference room with a laptop computer, and we project the document up on the screen, walk them through all 7 steps, putting particular emphasis on steps 2, 5, and 7. And inevitably, as we're going through the principal study questions, the EPA or the state will chime in of, oh, I think another question we need to consider is this, or another question we need to consider is that. And so you're then adding those in with your laptop computer on the fly. This continues to build that teaming relationship. The next step then, you'll make revisions out of the conclusions from that meeting to your document, and then send it out for formal review by the regulatory agencies. Make revisions based on the comments, and then once the document's all cleaned up, walk the regulators through again the document and how you address their changes to get their final buy-in. Then you issue the final report, the DQO summary report, and then begin preparing a sampling and analysis plan. So now I'm going to briefly go through the 7 steps of the EPA QA-G4 guidance manual. Step number 1 is designed to clearly develop a problem statement. Here's where we identify the contaminants of concern. We develop the conceptual site model. Step 2 is where we identify all the questions that need to be answered. At the bottom there, I've presented an example principal study question out of my textbook that follows the format provided by the EPA QAG4 guidance manual. This is the very most important step in the DQO process because if you miss a question, it will impact all the remaining steps of the process. Step 3 identifies the specific types of data needed to resolve each of the principal study questions, as well as the quality of data that's needed. Step 4 defines the vertical, horizontal, as well as the temporal boundaries of each of the principal study questions. Step 5 develops what we call decision rules. I provide an example here of a decision rule taken out of my textbook that does follow the format provided in the EPA QAG4 guidance manual. Step 6 identifies the principal study questions that require a statistical versus a non-statistical sample design. And then step 7 develops multiple sample design options that satisfy all the requirements of the first 6 steps of the DQO process, and then selects the preferred design. I have provided a list of screening methods that should be considered when developing sample designs to help keep your costs down. These are all taken out of my textbook. For example, aerial photography, using soil gas sampling, either passive or active, a variety of different types of surface or downhole geophysical surveying techniques, pipe surveying, ribbon sampler, things of that nature. This table here presents different types of media sampling methods taken out of my textbook for shallow soil and sludge, deep soil, sediment, surface water, waste liquid, groundwater, air, etc. Each one of these different methods has its own advantages and disadvantages. So those are some that should be taken into consideration. This slide now presents visual sample plan statistical software. This is a free software package that was prepared by the Pacific Northwest National Laboratory and is highly accepted and recommended by the Environmental Protection Agency. Version 7 is the most current version. This is basically statistics for environmental dummies. It's very, very easy to use. It makes sense. It's very well done, and you should consider that. The last slide that I have here is the reference to my textbook that provides further guidance on how to go through each of the steps of the DQO process, as well as multiple sample designs and things of that nature. So at this point, I will turn the talk over to Trip Fisher now, who talk more about remedial technologies.
Thank you, Mark. Hello, I'm Trip Fisher with Brownfield Science and Technology, and I will be presenting remedial strategies, processes, and technologies, which are also collectively known as remedial action. Environmental remediation includes all of the processes that are required to address chemicals that are released to the environment. I say address and not just clean up because, as we'll learn, there are remedial strategies which don't necessarily involve physically removing the chemicals from the environment. Remedial strategies may be required for acute releases such as tanker spills or storage tank ruptures, or they can be for historic releases which are decades or maybe decades old. Either way, in order to achieve success, goals should be identified and key processes should be followed. With acute releases, these goals and processes are oftentimes preset through rigorous planning and training because time is of the essence. You're trying to plan all of that ahead of time so that you can adequately address the acute release when it happens. With older releases, the goals and processes are usually identified following a thorough environmental assessment. And this will be the focus of this presentation. Generally, remediation goals, I group them into two categories: risk-based goals and non-risk-based goals. Risk-based remediation goals are designed to protect humans and animals, organisms from adverse chemical exposure. In order to have risk, you need three things: a chemical, a pathway, and a receptor. The chemical is what actually causes harm. So this is typically the chemical release. The receptor is the human or ecologic receptor. And finally, the pathway to complete the exposure of the chemical to the receptor. The pathway is the means by which the chemical can be either inhaled, ingested, or absorbed into the body. And to eliminate risk, we have to eliminate at least one of these three criteria. So in terms of remediation goals, we can clean up a chemical source so that it's no longer a threat by removing it entirely or reducing the concentration to a safe level. We can replace a water supply that's impacted with a chemical to eliminate it as an exposure pathway, or we can remove a receptor entirely. An example of this would be an evacuation if a chlorine gas release occurred. The second set are non-risk-based goals. The non-risk-based goals are oftentimes drive remediation strategies. These can actually be sometimes more stringent than risk-based goals. An example may be a very risk-adverse business that doesn't want their property to be chemically impacted, either the soil or the groundwater, regardless of whether it poses a risk or not. As previously presented, the remediation design process starts with the development of comprehensive conceptual site model and site characterization. The process is to identify the degree and extent of contamination and the media, soil, groundwater, or soil gas that's impacted. This is the point at which remediation goals are established. The next step in the process is typically a technology screening. This step takes the full suite of remedial technologies and whittles them down to 2 or 3 that will be the most applicable based on the goals and limitations identified during the conceptual site model development. In practice, this is oftentimes intuitively performed during the site characterization process and is finalized once the remedial goals are actually set. So as you're developing your conceptual site model, you already begin to think about what technologies will work and won't work. Next, if applicable, is the pilot testing phase, where we take the possible remedial strategies identified in the screening process and either on-site or in the laboratory or on paper evaluate the cost and performance of those technologies. This could be a bench scale test in a laboratory or actually operating a small scale version of the total remediation system for a limited time on site, and then extrapolating what the long-term costs and effectiveness would be. The final step is the selection, the design, and installation, and ultimately monitoring of the remedial strategy. This process can sometimes involve regulatory oversight, permitting for the installation of wells or air treatment, water treatment, discharge. Once installed, the remedial strategy should be monitored for performance and measured against the expectations outlined during the design process. And finally, most importantly, the remedial strategy should be adjusted and routinely optimized for performance. I group most all remedial strategies into 3 categories. Bulk mass removal, that's like a championship boxer. They're designed to knock the chemical out by physical means. These methods include things like digging, pumping, where you pump out contaminated groundwater, any way of physically removing chemicals from the ground with pumps, vacuums, those sorts of things. The second group involves changing the phase or chemical structure of the chemicals that you're trying to treat. With this group, we use chemistry or biology to change the chemicals to less threatening forms. We can also use remedial technologies to change the state the chemicals are in to make them more recoverable. An example of this is when we force chemicals out of groundwater and into soil gas so that they can be vacuumed out of an airstream. We can also do things like apply heat to vaporize chemicals. We can inject oxidizing chemical compounds such as hydrogen peroxide, ozone, sodium persulfate to change the chemicals in soil and groundwater into harmless compounds such as carbon dioxide and water. This process is known as in situ chemical oxidation or in-place chemical treatment. The final technology listed here is biologic treatment or bioremediation. This is a process in which aerobic or anaerobic organisms are used to remove or degrade chemical compounds into less toxic or non-toxic substances. Most of the chemicals being remediated can be viewed as an energy source for the organisms. The ease at which these organisms can access that energy will determine the likelihood that the compound will be remediated by biological processes. And finally, the third group of remedial strategy are containment strategies, like an offensive line. They're there to block out the contamination. These are typically used when it's not feasible to remove or treat the chemicals, and we simply want to contain the chemical release to a certain area. We can do this by creating a subsurface barrier wall that blocks out the chemicals from migrating past a certain point. Another way we can do this is through what's called in situ stabilization, a process where through physical mixing of soil we can solidify the soil by combining bonding materials to solidify the chemically impacted soils in place. As you've seen, there are several remediation strategies available to us and many factors that go into selecting one. In addition to achieving remediation goals and doing so in an appropriate time frame, the remediation strategy must also be implemented within the physical limitations of the site. Remediating a property that is vacant with all its structures raised is obviously a lot different than remediating a site that contains a full functioning business with active utilities. Power concerns are also a factor. If I have a power demanding system, do I have the power available to me that I need, single phase or three-phase power? Or if I am designing a system that generates waste like contaminated soil, water, or air, what are my treatment and disposal options? Can I treat on site, or do I have to ship all waste that I generate? Are there safety concerns such as high traffic areas or frequent trespassing? Or are there community concerns such as odors, noise, or traffic? Sometimes an excavation, opening up an excavation can release vapors and odors into the air, and that could be a concern. Should I hold, or do I have to hold, a public meeting to make sure that our strategy is acceptable to the public and the regulatory agencies? Some regulations require these types of meetings. What challenges does the geology of the subsurface present? How will that impact our strategy? Are we remediating groundwater and bedrock or in sand or clay? And finally, costs. What are the life cycle costs of the remedial strategy? Is an aggressive technology which demands a lot of upfront costs acceptable to the remediation goals of the client? Or does the client need a less aggressive, less timely approach but still accomplishes our remedial goals? The key to selecting a remedial strategy is finding the most capable technology for meeting all of the criteria presented here. And finally, success. In the end, we all want success. What defines success? First off, knowing that you did select the most capable technology and you're implementing it in the most capable way. You have to select metrics and milestones by which you can gauge your success. Sometimes it's necessary to have your remediation strategy be comprised of multiple technologies or a treatment train of technologies. For example, bulk removal of contaminants may be most effective in early stages of remediation, but you reach a point where it's no longer cost effective. If at this point you still have not reached your remedial goals, you may have to switch to a different technology like in situ technologies or in-place treatment. It is important to optimize whatever technology you implement. When you think about it, most of the time we are trying to remediate something. We can't see it. It's not like we're trying to clean up a mess along the side of the road that just recently spilled. We have to constantly measure the systems, evaluate the data, and make adjustments and see what the system is telling us in terms of its success. And finally, and most importantly, we have to keep it safe. If we're all doing this cleanup to protect the public, then it doesn't make sense to implement a remedial strategy that isn't safe to begin with. And finally, my last slide, I put up some resources that are good resources, mostly peer-reviewed and or industry standard development organizations that will help with various types of remedial strategies and remedial technologies. First is ASTM International with their 3 committees dealing with environmental, soil and rock, and water. The standards under E50, D18, and D19 all have to do with environmental practices or site assessment practices. The second is ITRC. If you're not familiar with ITRC, it's the Interstate Technology and Regulatory Council. They have many teams in ITRC, from light non-aqueous phase team to dense non-aqueous phase team to sediments and many others. And they have guidance documents, tech reg documents that are very good, as well as online trainings that can help with remedial strategies and remedial technologies, and they're quite current. And then finally, US EPA Clue-In website. It's an excellent resource for multiple guidance documents and or trainings. It's a good portal for all of those types of trainings. And with that, that concludes my talk, and I'll send it back at this point.
Okay, thanks, Chip, and thanks to the other presenters as well. Thank you very much. We've had a number of questions come in from the audience during the program, so we're going to try to get to those. To start out, a question came in about biorefineries for biofuels and bioproducts. As a lot of the world sort of moves toward bioeconomy as an emerging field. So the question is, what do the speakers consider as the most important challenge for process safety in that emerging field in biorefineries, and then how can you address that challenge or those challenges?
Do you want me to have a go at that?
That would be great.
This is Ian Sutton. From a process safety point of view, it probably doesn't make a lot of difference. The principles of process safety apply very widely. I actually have worked at Hanford Nuclear. Almost any organization that has a process of some kind, the principles apply. My only thought would be that bioprocesses probably involve more environmental problems than the more conventional processes.
Okay, thanks, Ian. We'll move on to another question. We had a question which says, what is the difference between the risk assessment and the 3D site assessment in the pedagogical model?
Ian, can you answer that one?
No, I'll pass on that one. That's you or Trip.
I can't. I don't have.
I mean, I can talk about risk assessment in a broader sense, because I'm not familiar with this 3D terminology. I mean, the whole point about risk assessment is that risk can never be zero. It's one of the huge public relations problems, that it can always happen, whatever it is. And one of the things that industry has wrestled with for decades is this whole issue of acceptable risk. Because once you've determined a value for acceptable risk, you've actually said that accidents are inevitable. And so I don't know if this is answering the question, but what I've seen in the last few years is that both agencies, regulatory agencies, and companies are just not talking about that anymore.
I might be able to answer this one also a little bit from my perspective of site assessment. Of course, we do collect analytical data during our site characterization that is used for risk assessment, and clearly defining the three-dimensional distribution of the contamination within the environment is critical for exposure to human and ecological health. So I would say that's one important aspect for defining that three-dimensional aspect, is just to understand how the exposure happens.
Okay. We'll maybe move on to we're going to try this one. Of the 7 steps, the question is, which one do you think is the most important? And for numbers 2, 5, and 7 in the steps, can you explain a little bit why those are included or why those are important?
Okay. Yes, this question is referring to the EPA 7-step data quality objectives process. And I did identify DQO step 2 is particularly the most important step in the process, because it's the one that identifies all the questions that need to be answered and then identifies the alternative actions that would be taken after the question is answered. Those two are rolled up together into what we call decision statements. The reason it's so important is if you don't ask the question, you're not going to end up collecting the data that you need to answer the question, of course. You will mobilize out into the field, and you will end up collecting data but missing the collection of data to answer that question. You might remember a month or 2 later, oh, I forgot about that portion of the study, and that would require a remobilization at added cost and a delay to the schedule. Step 5 in the DQO process is particularly important. That's where the decision rules are developed. And a decision rule basically integrates what we call the parameter of interest, which would be like the mean concentration of a contaminant or the maximum concentration of a contaminant, along with the action level and the alternative actions. And so it rolls a bunch of the pieces together from the other 7 steps of the DQO process. And then finally, step 7 is particularly important because it presents the designs themselves. And when you sit down and talk with the regulatory agencies, of course, they're particularly interested in the design that you have come up with at the conclusion. So that's basically why I highlight steps 2, 5, and 7 when I meet with the regulatory agencies.
Okay, thank you. Another question is this: is a registered professional engineer required by the EPA or another environmental regulatory group to lead the ESA or EIA project team? And if so, is there a specific legal reference?
I think this one is relating to my talk as well, and I think it's supposed to be referring to the Data Quality Objectives project team. I apologize if I not reading this question right, but here at the Hanford Nuclear Reservation, we are not required to have a registered professional engineer that's leading those tasks. It just really needs to be the facilitator, needs to have just excellent communication skills. They have to have a good understanding of the scope of work. But really, probably the most important aspect of that is developing those positive relationships with the regulatory agencies and building their trust.
Okay. We have another one that I think relates maybe a little more to Trip's presentation. The question is, would you be able to say a little bit more about the costs of each remediation technology or each remediation technology type?
Sure. Costs, that's always the tough one in all of this, really, because it's such a sliding scale depending on what you're trying to clean up and the limitations on site that you're trying to deal with. There are more aggressive technologies than others and that have more upfront costs. And just to kind of throw out an example of what I'm talking about, if you could completely remediate a site by removing 2 truckloads of soil through means of excavation, you could imagine that would be a lot less expensive than if you were to build and design some sort of treatment system to treat that relatively small quantity of soil. That would be a much more expensive way. However, if you increase the scale of the contamination at that site, then all of a sudden excavation, and especially the depth, all of a sudden the excavation becomes a lot more expensive, and that design system becomes a lot less expensive. So depending on the quantity, the depth, the accessibility, the contamination that you're actually going after, really depends a lot on the cost and which technologies become expensive. Some technologies may be expensive on one site but not on another, and that's where the life cycle costs really come into play with a good design up front. If there are a few technologies that can adequately address contamination to your goals, it should be presented to you as a client in a life cycle cost analysis of what you're looking at, what the upfront costs are versus long-term costs. There are technologies that could be very expensive up front, but it will get over with much quickly, which will reduce reporting and regulatory oversight and routine sampling and all of that, whereas a longer-term, 15-year cleanup would have all of that included and could become more expensive, but the costs are spread out farther. So it's a tricky question. It's a sliding scale, and there's a lot of factors that go into that.
Okay, thanks. There's another question that could be interesting. It's whether there are models that are specific for different regions of the world, geographic regions. An example, the questioner says, could be contamination of a chemical that might be more hazardous at certain temperatures, which maybe I assume might mean different climates. So anything geographically speaking that's a consideration?
I'll take a shot at that. I think once we're below ground contamination, below ground, below a certain depth, it often doesn't. The location doesn't matter so much, except for in remedial terms. If you're removing water, from the ground, in colder climates, there are air treatment technologies and pumping technologies that you'll have a real hard time with, just due to freezing of condensate and pipes, and they're just a lot more maintenance. They require a lot more maintenance than would be in areas that wouldn't freeze. As far as models go, the only models that I've ever worked with or that I'm familiar with that take those concepts into consideration are things like air models, different densities of air, but most of those models aren't specific to certain areas. They're just models that are adaptable to whatever area you may be. You just put those parameters, change those parameters based on the climates into them. But anything specific to certain regions, I'm not familiar with.
All right, thanks. So this one may be directed at Mark. Mark, what was the question is, what was the link to the visual sample?
Okay, that's referencing the visual sample plan statistical software. I would just suggest go to Google and just type in visual sample plan, and that will be the top web page that pops up. It will go right to the Pacific Northwest National Laboratory page that's right for visual sample plan, and there's a link right there where you click on it and can download the software. So yeah, I encourage you to use it. It's awesome.
Great. Thanks very much. So we've actually reached the end of our scheduled webinar time here. So if there are remaining questions, we'll take a look at those and see if we can respond offline after the program. So once again, thanks for the presentations.